Great. So we'll be presenting about Shepherd, Stripe's new feature engineering platform. We'll cover topics related to the online and streaming portion of our architecture, explore how we've leveraged the open source Chronon project, and discuss the control plane that we created to accelerate feature development. Before diving into Shepherd, let's first talk about Stripe and our use of ML. Stripe is a financial infrastructure company that processes over $1 trillion in payment volume every year. At this scale, leveraging ML across our product line is crucial. As you can imagine, one of the main use cases for ML is preventing payments and merchant fraud. Our models cover not only traditional credit card transactions, but also a variety of other payment methods, including those specific to certain countries. Given our scale, models must operate under strict latency and freshness constraints. Detecting and responding to fraud in real time is essential to protecting our users and maintaining the integrity of our financial ecosystem. To satisfy Stripe's growing needs for machine learning, we decided to build a new ML platform in 2022. Given the adversarial nature of the fraud space, this platform needed to enable quick feature iteration, backfill of historical data, and fast deployments. It also had to support batch features and streaming features with low latency and freshness, both in the order of milliseconds. After considering a number of alternatives, we decided to partner with Airbnb, who also presented at this conference, to adopt Chronon and modify it so that it could work with Stripe's databases and infrastructure. Together, we open sourced Chronon earlier this year, and we're now co-maintainers of the project. The first thing I'd like to walk you through is a simplified example of how a feature is defined in Shepherd using the Chronon API. We'll build upon this example for the rest of the presentation to demonstrate how our streaming infrastructure operates and how data flows through the system. So the feature we'll be creating is a simple streaming feature that you might encounter in a payment fraud model. It corresponds to the amount of money charged on a credit card over the last day. The first step is to define our source. Because Shepherd uses a Lambda architecture, as we'll discuss soon, we need both a table and a Kafka topic. From this source, we only really care about two fields, the card ID and the dollar amount. Here you notice I'm using a cast. This cast comes from Spark SQL, which can be used across Chronon and is applied the same way both online and offline, as we'll see in just a moment. And that's it. So now we can use this source to define some aggregations. To define windows and aggregations, we use the group by API. The feature we want to represent is the amount of money charged on a card over the last day. To create this feature, we will key the event stream on card ID, define a sum operation on the amount in dollars over a one-day window. If we wanted to add more card-related features, we could just add more aggregations or more windows to that list. And that's pretty much it. In practice, you would also use the join API, which allows combining multiple group bys and running point-in-time correct backfills. From here, Shepherd will automatically compile this code into batch Spark jobs and streaming Flink apps and enable the features to be served in low latency. So now let's go over a simplified version of Shepherd's architecture. As I mentioned earlier, we use a Lambda architecture. So we have Flink apps running continuously and Spark jobs running periodically. Both these jobs produce intermediate data and store it in very low latency key value stores. On the online side, a stateful Flink app processes events from Kafka and pre-aggregates the data based on the group by and source definition, similar to the one we just saw. It then writes this data to a memcached-based KV store. The offline side is similar in principle. The Spark jobs process historical data from sources like iceberg tables and write the results to a key value store. Then at serving time, a dedicated service fetches, merges, and finalizes data from both stores, and the feature vector is served to users. In the following slides, we'll delve a little deeper into Flink and the serving side of the system. So if we're running a Flink application to produce streaming data and Spark jobs to produce batch data, how do we ensure consistency across these two platforms? Well, we essentially just aim to run the same Chronon code in both places. The noteworthy part here is that Chronon supports Spark SQL in its feature definitions. So we need to run Spark inside of Flink. We achieve this by directly utilizing Catalyst, Spark's query optimizer. At the core of this functionality is Cronon's Catalyst util class, which extracts the execution plans from Spark and creates transformation functions that can be executed in Flink or anywhere else at low latency. This is a very interesting part of Cronon and Shepherd, but it's pretty complex, so we won't go into too much detail here. But fortunately, Cronon's open source, so if you're really curious, you can just go and check out the repo. Now let's go into a little bit more detail on the streaming system. For this part, I'll compare the default Cronon architecture, which uses Spark streaming, with the tiled Flink architecture that we developed at Stripe and open sourced. So as I said, the default Cronon architecture uses Spark streaming, not Flink. This approach simplifies achieving online-offline consistency because it's all just Spark, and it's sufficient for most organizations. Here, the source of a feature is calculated using the Spark streaming job. If you remember the one we just created, the Spark streaming job would decode the events, extract the card ID and the amount in USD, and then execute any Spark SQL that is included in that definition. Those transformed sources would then be stored in a key value store. Then at serving time, Cronon would fetch all the necessary events to fill that defined window, like the one-day window we created, perform the aggregations defined in the group by, and construct the final feature vector. Again, for most organizations, this architecture works really well. However, you can imagine the limitations at scale. For example, if a corporate credit card sees heavy activity with 10,000 purchases in a day, serving latency would be quite high. Fetching and aggregating many thousands of events every time a model needs features is computationally expensive. So, to solve these scaling issues, we adapted Cronon to use a tiled architecture. The core idea here is to move computation from the feature retrieval side to the feature computation side, thus improving time complexity at serving time. The most significant change is that we pre-aggregate the events in Flink and store the intermediate data as fixed length tiles in the KV store. Instead of just evaluating the source, Flink also calculates the aggregations defined in a group by. These tiles are kept in Flink's memory while they're being calculated. And as events arrive, Flink processes the selects and the filters defined in the source and updates the in-memory pre-aggregates based on the group by definition. It also writes out the tiles to the KV store with every event. So for example, in the feature we created earlier, Flink would maintain tiles containing the sum of amounts for each credit card it has seen recently. This way, instead of storing one entry in the KV store for each event that comes into Kafka, we only store at most one tile per period of time. This approach significantly reduces the amount of data that needs to be fetched and aggregated during serving time, thus improving scalability and reducing serving latency. The end-to-end flow here, or feature freshness, is also quite fast despite the additional work. The delta between an event landing in Kafka and data being updated in our KV stores is almost always lower than 100 milliseconds. So to help visualize these two different architectures, let's walk through a real example. Imagine the 6 following events land in Kafka, each with a card ID and an associated amount. In the untiled or default Cronon architecture, Spark would store 6 individual entries in the KV store, similar to what we see here. In contrast, in the tiled architecture, Flink would pre-aggregate the sum of these events and store the intermediate result as a tile. So for example, the 2 card A events before 1 o'clock would become a single sum value. Then when serving features, the fetcher would gather and merge the relevant tiles. So with this tiled approach, we were able to significantly reduce feature retrieval latency. In most cases, feature vectors containing many hundreds of features can be served in single-digit millisecond latency. As I showed in that diagram earlier, feature serving in Shepherd is done through a dedicated service that runs the Cronon fetcher. And to illustrate how this works, let's walk through an example of feature serving. Let's say it's 1:30 a.m. and we want to retrieve features for the group by that we previously defined using card A as key. Because we use a Lambda architecture, to serve streaming features, we need to fetch both offline KV store data and streaming KV store data, and then merge them together. So in this example, let's say the batch KV store contains the sum of 200, for example, and the streaming store contains two tiles, one containing value 35.99 and one containing value 40. To serve this feature, the fetcher would fetch all this data, merge the amounts, and compute the final feature vector 275.99. And that's essentially how it works. It's kind of a simplified version, but in theory, in practice, it's kind of how it works. There are several optimizations that we implemented on top of this architecture to further improve scalability, such as using multiple tile sizes and leveraging an in-memory cache. If you're interested in learning more about these optimizations, feel free to reach out to us in Slack or via email. And I'll now pass it off to Divya to discuss our control plane and how it's significantly sped up feature development at Stripe. I think you can share your screen, Divya.
Cool, thanks, Kaio. So we've unlocked the ability to serve large features at low latency, which is a critical requirement for our charge path use cases. However, we found that onboarding new use cases onto Shepherd can be a toilsome process that requires numerous manual steps. I'm going to be talking about the Shepherd control plane, which we've built to automate our infrastructure management and accelerate feature development at Stripe. Onboarding new teams to using Shepherd can be a long, toilsome process for the feature computation team. There are many manual actions required, which does not scale well as we expand the number of ML use cases at Stripe. For each new team or business use case using Shepherd, we manually provision a new Flink application to process real-time streaming data for the team's online feature groups, which are another name for group bys, as we saw earlier. This requires setting up all of the Flink app scaffolding, provisioning Zookeeper and S3 resources for the application, ensuring we have enough capacity to process all of the feature groups, and configuring alerting for the new app. Additionally, running all feature groups owned by a team on one Flink application results in issues with noisy neighbors that can bring an entire app down if any feature groups are encountering problems, and degraded feature freshness as ML engineers add new feature groups and the app is unable to handle the additional load. We've ended up having to provision multiple Flink applications for a single use case, which both blocks our users from serving new streaming features and makes it difficult to scale Shepherd as a platform. Some additional steps that are required to onboard teams onto Shepherd include provisioning a new key value store for our Flink applications to write data to, registering the batch dataset for every new feature group that is brought online, and creating a new Shepherd API tier for feature serving isolation, which also requires manual scaling to account for growth in traffic. You can see in this graphic the number of Jira tickets our team has open every day to manually register these batch datasets for new online feature groups. Typically, all of this setup is a 1 to 2 week cross-team effort, during which our users cannot serve their new online features. Managing the scale of this infrastructure also requires ongoing monitoring and tuning from the feature computation team, which again poses a scalability issue for Shepherd. To combat the amount of manual effort necessary by our team to onboard new users, as well as speed up feature development at Stripe, we've built the Shepherd control plane to empower ML engineers to self-service the creation and maintenance of their infrastructure for model training and inference. There are a few major components we built to make Shepherd an easy-to-use self-service platform with automated infrastructure management. First, we need to understand the concept of a storage pool. Each Shepherd use case at Stripe maps to its own storage pool, which is an abstraction we use for managing the use case's infrastructure. Storage pools are attached to feature groups, as we can see here. Each pool contains information, such as which feature groups it should manage, the amount of traffic expected to read these features, the criticality of the use case, and which regions we want to serve traffic in. The pool uses the feature groups configured to determine which batch datasets to register. Additionally, each storage pool will create its own key value store and Shepherd API tier in order to promote feature serving isolation, which is critical for our users, especially for our charge path use cases. We were able to benefit from using Stripe's programmable infrastructure configuration engine, also known as SPICE, for creating our storage pool abstraction and control plane. In our current Shepherd architecture at Stripe, our ML models read from our feature service via an API tier, which calls the Chronon fetcher under the hood. The fetcher reads from our KV store and batch datasets to compute the feature values. All of this infrastructure was previously manually provisioned and managed. The first piece we built as part of the process of onboarding onto Shepherd with the control plane is our custom CLI tooling. With easy-to-run commands, users can create and update their storage pools, which will auto-generate the code for creating and scaling a new Shepherd API tier based on the user's specified expected traffic, adding and removing feature groups from the storage pool, as well as updates to any other pool configurations, and finally managing the deployment ordering for pools and API tiers based on the configured criticality of the pool. This means users can specify a new region on their storage pool via the CLI tooling, and all of the infrastructure will be automatically provisioned in the new region with no manual work from ML infra teams needed. Each storage pool has its own service, which is auto-deployed daily. During these deployments, the Shepherd control plane manages all of the infrastructure for the pool, which includes creating a key value store for the storage pool, provisioning batch datasets for each online feature group in the pool, and deploying an individual Flink application for each online streaming feature group. The control plane uses temporal workflows and is built to be idempotent, resilient to outages, and manages the scale of all Shepherd infrastructure. Our integration with the Flink control plane has allowed us to automatically provision a Flink app for each individual feature group. Having this isolation results in fewer correlated failures, better feature freshness, and ultimately improved model performance. The Flink control plane manages scaling the application based on heuristics such as the job graph size and configured parallelism, so managing the scale is not an issue for our team anymore. You can hear more details about the Flink control plane and how it was built at Flink Forward next week. Stripe operates as a multi-region company, so high availability and feature freshness are critical for our large use cases. Via the control plane, we are able to automatically enable cross-region replication on the pool's key value store for high availability in case of regional lag, as well as check the scale of the cluster to prevent it from becoming overloaded as we spin up additional Flink apps. The control plane notifies teams of any manual actions that are necessary by automatically provisioning Jira tickets, and also notifies pool owners of any important actions taken by the control plane via Slack. Additionally, we were able to use the storage pool abstraction to create a custom internal UI for tracking pool status changes and metadata. This makes it easy to understand what features are being used by which teams, as well as easy to track the pool deployment progress. We are currently in the process of rolling out the control plane to all of our Shepherd ML workloads at Stripe. The control plane allows ML engineers to rapidly develop new online features without being blocked by the manual scaling and provisioning requirements needed by our team. Additionally, our users are able to benefit from high availability on their Flink applications and improved feature freshness via automatically enabled cross-region replication. This combination of accelerated feature development, reduced toil for the ML infrastructure teams, and improved feature freshness contribute to better model performance and ultimately growth in fraud loss savings for Stripe. We are continuing to develop on the control plane to add automation and safety guardrails where needed, and ultimately make Shepherd an easy-to-use self-service platform for ML engineers at Stripe. Thank you.